Okay, by this point we should have enough information, we should know enough to be able to tackle a question like this. This is question 12 from the 2019 Semester 2 exam. The total question is worth 15 marks and we're going to do all of it. This should give you an indication as to the level of question that you should be able to answer, and go through, do this with me and make sure that you kind of know how I'm doing all the steps that I'm doing. Uranium-238 is a radioisotope and an alpha emitter. The data below will be of use to you in this question. You will also need to refer to the periodic table in the formulae and constants sheet. Note, and this is an important note, when performing calculations in this question, do not round to 3 significant figures. Okay, so that doesn't mean our answers aren't going to be in 3 significant figures. It just means that our calculations, before we get to our answer, we can't round them or we will make errors. Okay, so here we have a table where we have 5 different particles and their atomic masses. Question A. Use the above data to perform a calculation showing that the mass defect for a uranium-238 nucleus is about 1.90 U. Okay, the mass defect for a uranium-238 nucleus. That means that it's asking us to calculate when we add up all of the individual nucleons, the protons and neutrons that make up a uranium-238 nucleus, how much mass is lost when those nucleons all form together to form the one big nucleus. That's the mass defect. So to do that, we need to know, first of all, how many protons and how many neutrons are in a uranium-238 nucleus. Uranium-238. We look on the periodic table and we find that it's got an atomic number of 92. That means it has 92 protons. And since its mass number is 238, we do 238 minus 92 and we calculate that it would have 146 neutrons. So now, the sum of the masses of the individual parts that make up this nucleus. We need to add together the mass of all the protons and all the neutrons. So the mass of the parts is going to be equal to 92 times the mass of a proton plus 146 times the mass of a neutron. And I'm getting these numbers from the table. When I do this calculation, I'm going to get a mass of 239.93466 U. The mass defect is going to be equal to the mass of uranium-238 minus the mass of the nucleons that we just calculated. So that is, the mass of uranium-238 is 238.05. Sorry, hang on. I've made a small mistake there. These need to be the other way around because, as you can see, the mass of the individual nucleons is, of course, as we expect it to be, greater than the mass of uranium-238. So the mass defect is going to be the mass of the individual nucleons, which is 239.93466, minus the mass of uranium-238, which is 238.05079, which gives me a mass defect of 1.88 U, which equals approximately 1.90 U, as the question said it would. Question B. Hence, calculate the binding energy for a uranium-238 nucleus. So we have, on our physical constants and formulae sheet, we have a mass energy equivalence. 1 U is equal to 900 and sorry, you can't see that, 1 U is equal to 931 mega electron volts. So if I have 1.9 U, the binding energy is equal to the mass defect times 931, which is equal to approximately 1.90 U multiplied by 931, which gives me 1.77 times 10 to the 3 mega electron volts. The number that you actually get when you put this into your calculator won't be exactly 1.77 by 10 to the 3. I've rounded my answer to 3 significant figures. But make sure that you're going to keep your original answer in your calculator, or you write it down somewhere, because remember, in our calculations, we shouldn't be rounding to 3 significant figures. So we might need to use that number later on, which means we should be keeping these numbers either stored in our calculator or written down on the page in case we need to use them later on in the question. Okay, part C. Using your answer to part B, calculate the binding energy per nucleon for a uranium-238 nucleus in mega electron volts. If you are unable to calculate an answer for part B, then use a value of 1,750 mega electron volts. We don't have to use that because we did get an answer for part B, so the binding energy per nucleon is equal to the binding energy divided by the number of nucleons. In the previous question, we calculated the binding energy to be 1,768.9. We rounded that before to 1.77 by 10 to the 3, but now I'm writing it in its full. Mega electron volts divided by the number of nucleons in uranium-238 is, of course, 238. That will give me a binding energy per nucleon of 7.43 mega electron volts. And that is per nucleon. Question D. Nickel-62 has one of the highest binding energy per nucleon of any known isotope, with a value of 8.7945 mega electron volts. Compare this value with the corresponding value for uranium-238 calculated in part C. Use this comparison to compare the stability of a nickel-62 nucleus versus a uranium-238 nucleus, and to explain their contrasting properties in this regard. As part of your answer, you must discuss the presence of the strong force in each nucleus. Before I answer this question, I'm going to go through and underline each important point that I'm going to have to address in my answer. So first of all, it wants me to compare the stability of nickel-62 with uranium-238. It wants me to use that to explain their contrasting properties, and I must discuss the presence of the strong force as well. So 3 things that it's asked me to talk about. Notice that this question is worth 3 marks. So if I can use each of these 3 things in my answer, then I should be hitting every point I need to get the full 3 marks for the question. The best way to answer this question would be to say these 3 things. First of all, you would want to say that the strong force comes from the binding energy. So binding energy is the source of the strong force, which binds nucleons together and why does it need to bind nucleons together? That's, of course, to overcome the electrostatic repulsion. In the previous video, I referred to this force as electromagnetic. It's also, perhaps in this particular case, more commonly referred to as the electrostatic force, because it's the repulsion force between the 2 protons that are both sitting there stationary in the nucleus, or basically stationary anyway, whereas we would use the electromagnetic term more when we're dealing with, lots of moving parts and things, but either one is fine. So I've spoken about the strong force. I've said that the binding energy is the source of the strong force, and I've explained what the strong force is. It binds nucleons together to overcome the electrostatic repulsion, which forces protons apart. The second thing I want to say is now I want to compare the stability of a nickel-62 nucleus versus a uranium-238 nucleus. So I would say that since nickel-62 has a higher binding energy per nucleon, it is more stable. Than uranium-238. So I've compared the stability as it asked me to, and now I'm going to use that comparison to explain their contrasting properties. So I've explained that nickel-62 has a higher binding energy per nucleon, which makes it more stable, and that is why uranium, so hence uranium-238 is a radioisotope, but nickel-62 is not. There we go. Three things. I've spoken about the strong force, I've compared their stability, and I've used that comparison to explain their respective properties. Full 3 marks. Last bit of this question, part E. It reads, as stated earlier, uranium-238 is an alpha emitter. Complete the nuclear equation below for this transmutation. Show the chemical symbol, atomic number, and mass number for the missing product. So if we look at this, equation here, we've got uranium-238 emitting an alpha particle, helium, which has an atomic number of 2 and a mass number of 4. What we need to do is then we need to look at our periodic table, and we need to find, if we take 2 protons out of uranium-92, then what are we left with? We're left with an atomic number of 90. We use our periodic table to find out that that would give us the element thorium, which has an atomic number of 90, and we have taken away 4 nucleons in total, which means our new mass number will be 234. Now, the second part of this question, use the data in the table provided earlier to calculate the energy released in joules during the alpha decay. Okay, so we need to use the information from this table here, because we need to know what the total mass on the left-hand side and the total mass on the right-hand side is. So the mass of uranium-238, we read that straight off the table, and we get that that is 238.05079. Now we need the mass of the products, or the whole right-hand side, the products, the thorium-234 and the helium-4. So what we get is, we get thorium-234 has a mass of 234.04360, added to the mass of the helium-4, which we use our table to find out that that is 4.00260. When we add those two together, we should get a mass of 238.0462. Notice that the mass of uranium is greater than the mass of the products. And that is because if we go back to that graph we were looking at in the last few videos, uranium is all the way over here. So as uranium splits into 2 smaller products, thorium, which will be pretty close to uranium, it'll be right next to it over there, and helium-4 all the way over there. As it splits into those 2 smaller products, we are climbing back towards iron-56, which means we're losing mass and converting it into energy. Okay, the mass defect is what we need next. So we've calculated the mass of each side. We now need the mass defect. The mass defect is equal to the mass of the, whichever one had the greater mass, which in this case is the mass of uranium-238, minus the mass of the products. So when I do 238.05079 minus 238.0462, I should get a mass defect of 0.00459 U. I'm then going to, it asked me to calculate the energy released. So I'm going to convert that into energy by doing the mass defect multiplied by 931. And that will give me an energy of 4.27329 mega electron volts. Okay, I'm almost done, but the question asked me to calculate the energy in joules. So my very last step will be to convert this energy into joules, and for that I'm going to take out my formula and data sheet again and find the conversion between electron volts to joules. 1 electron volt is equal to 1.6 by 10 to the negative 19 joules. Here I have 4.27329 mega electron volts. So if I multiply that by 1.6 times 10 to the negative 19, which gives me 6.84 by 10 to the negative 19, that's what I'll get when I do this multiplied by that in my calculator. This answer, 6.84 by 10 to the negative 19, that would be in megajoules, because this was in mega electron volts. Mega is 1 by 10 to the 6, so I would then need to multiply that by 1 by 10 to the 6 to turn that into 6.84 times 10 to the power of negative 13 joules. Of course, I could have skipped this step over here by, instead of multiplying by 1.6 by 10 to the negative 19, I could have just multiplied by 1.6 by 10 to the negative 13, which is a direct conversion from mega electron volts to joules, instead of going first to megajoules and then to joules. Either way, this is my final answer.